Today let's discuss questions related to surface areas and volumes of the given curves. So like in double integral, in these type of questions as well, first motive should be to draw the figure of the given curves so that you basically get an idea of the figure and you are basically able to interpret like which area or the volume you are supposed to calculate. So we'll try to draw a figure wherever possible. So let's start with the questions. So the question 1 says that using double integration, find the area lying inside this cardioid and outside the circle r equals to a. So we are supposed to find in the area that lies outside this circle but inside this cardioid. So first aim should be to draw the figure of this cardioid and the given circle. So let's do that. So if let's say this is my y-axis and this is my x-axis. So graph of cardioid is somewhat like this, and this point is basically 2a, 0, and here somewhere lies a, 0, and this point is basically 0, 0, and graph of circle r equals to a will be somewhat like this. And here it is minus a, 0, and this point is basically a, 0. So we are supposed to calculate the area, that is the area that I am shading, because it's the area that lies outside the circle but inside the cardioid. So this is our area. Now let's write the integration that we are supposed to calculate. So the integration will be required area will be area over double integration over area A r into d theta dr, and area is basically this, A is basically this shaded region. So it is integration, theta lies in let's find out the intersection point of these two. So it will be a equals to a into 1 plus cos theta. So that basically gives me cos theta equals to 0. So from here I got my theta equals to minus pi by 2 and pi by 2. So my theta varies from minus pi by 2 to pi by 2, and r varies from a, that is the circle, to this a into 1 plus cos theta. A to a into 1 plus cos theta r dr and then d theta. So if you see that because of symmetry, it's same thing as evaluating from 0 to pi by 2 two times, and a to a into 1 plus cos theta r dr d theta. So it is equals to 2 integration from 0 to pi by 2 r square by 2 limit from a to a into 1 plus cos theta d theta. So it is equals to, I can pull this 2 outside, so it will be integration from 0 to pi by 2. If I plug in the limits, it will be a square into 1 plus cos theta square minus a square d theta, which is equals to, a square is constant, so I can pull that outside the integration sign. Then integration from 0 to pi by 2, 1 plus cos square theta plus 2 cos theta minus 1 d theta, which is equals to a square integration from 0 to pi by 2 cos square theta plus 2 cos theta d theta, and cos square theta can be written as integration from 0 to pi by 2 1 plus cos 2 theta by 2 plus 2 cos theta d theta, which is equals to a square 1 by 2 theta plus sin 2 theta by 2 plus 2 sin theta, and integration from 0 to pi by 2. So if I plug in the limits, it will be a square into 1 by 2 times pi by 2 plus it will be sine pi, which is 0, and then 0 only, plus 2 times sine pi by 2, that is 1, minus sine 0, that is 0. So it is equals to a square into pi by 4 plus 2, which is equals to a square by 4 into pi plus 8. So this is the area that lies outside the given circle but inside the given cardioid. So let's move on to the next question. So next question says that evaluate the volume of solid formed by rotating this curve about the initial line. Now this is equation of a cardioid. So first let's draw it and see like what will be the curve that we'll get. So if this is my y-axis and this is my x-axis, so this is basically a cardioid and it is revolved around this axis like this, and the volume that is formed post revolving, we are supposed to evaluate its volume. So volume of solid formed by a rotating the curve around x-axis, because that's our initial line, is equals to, there is a direct formula for it, that is 2 pi by 3 integration from theta 1 to theta 2 r cube sine theta d theta. Now if you see that in our case r cube is basically this, r is basically this, a into 1 plus cos theta, so it will be 2 pi by 3 integration from theta 1 to theta 2, r is a into 1 plus cos theta, so r cube will be a cube into 1 plus cos theta cube sine theta d theta. So I can pull this a cube outside the integration sign because that's constant, so it will be 2 pi by 3 a cube integration from theta 1 to theta 2 1 plus cos theta cube sine theta d theta. Now let's see the value of theta 1. So if you observe that you need to complete the whole curve, you need to revolve it by an angle of 0 to pi only, because like when you'll start from this angle till the angle this point reaches here, this end will reach the other side, that will complete the whole solid. So we need to revolve it by an angle of 0 to 180 degrees. So it is equals to 2 pi a cube by 3 0 to pi 1 plus cos theta cube into sine theta d theta. Now in order to solve it, I can assume this term as u. So let us assume that u equals to 1 plus cos theta. So that give me du equals to minus sine theta d theta. So from here sine theta d theta is basically minus of du. So integration reduces to 2 pi a cube by 3. When theta is 0, u is basically my 2, and when theta is pi, u is 0. So it reduces to integration from 0 to 0 u cube minus of du, which is equals to 2 pi a cube by 3 integration 0 to 2 u cube du. Here I used a property of definite integral that says that integration from a to 0 fx dx is same as minus of integration from 0 to a fx dx. So using this property I got it, and if I evaluate it, it will be 2 pi a cube by 3 u4 by 4 0 to 2, which is equals to 2 pi a cube by 12, and 2 raised 4 minus 0 raised 4, that is 0 only, so it is 2 pi a cube by 12 into 16, and if I simplify it, it will be 3 4, that is 8 pi a cube by 3. So that's our final answer of this question. This is basically the required volume of the solid that will be formed post rotating the given cardioid around the initial line. So let's move on to the next question. So this question says that evaluate the triple integral which gives volume of solid enclosed between these two paraboloids. So they have given us the equation of two paraboloids, and we're supposed to evaluate the limit of the volume which is enclosed in between these two paraboloids. So volume will be basically, so first let's see what will be the bounds of z. So z lies in between 5x square plus y square and z equals to 6 minus 7x square minus y square, and these must be intersecting somewhere. So the intersecting region will basically tells us about the bound of x and y axis. So let's equate this and get the intersecting region. That will be 5 of x square plus y square is equals to 6 minus 7x square minus y square. So it gives us 5x square plus 5y square is equals to 6 minus 7x square minus y square. So from here you will get 12x square plus 6y square is equals to 6, and that simplifies to 6x square, or maybe we can divide throughout by 6. So it is 2x square plus y square is equals to 1. So this basically will tell us the limits of y and x. So let's evaluate the volume of the region. So volume of region or solid bounded by two paraboloids is it is equals to triple integration over, let's say R be the region that's bounded by these two paraboloids, into dz dy dx. So which is equals to integration, z is bounded by these two paraboloids. So let's write that first. It is 5 of x square plus 5 of y square, 7 minus 6 minus 7x square minus y square dz into dy dx. Now from here you can see that y basically lies in between under root 1 minus 2x square plus minus. So this is equals to, let me write it here only. So this is limit for z, and y is lying in between minus under root 1 minus 2x square to under root 1 minus 2x square, and from here only z lies in between minus 1 by root 2 to 1 by root 2. So this is basically like we need to basically evaluate this triple integral to get in the required volume. So like if you'll solve it in using these like using the Cartesian coordinates only, then it will be too complicated. So let's simplify it to cylindrical coordinates form. So let us assume that Rx is equals to Ry under root 2 cos theta, y equals to R sin theta, and z stays the same. So now we need to calculate the Jacobian as well. So the Jacobian will basically give equals to R by root 2. So that basically gives us dz dy dx equals to R by root 2 dr d theta dz. Now let's just plug in the values. So it will be integration from 0 to 2 pi, r varies from 0 to 1, and z varies from, like we can plug in x and y here. So it will be 6 minus 7 x square, that is r square by 2 cos square theta, minus y square, that is r square sin square theta, minus 5 x square, that is r square by 2 cos square theta, plus 5 y square, that is r square sin square theta, and here we have dr d theta, and there is Jacobian as well, that is r by root 2. So it is equals to integration from 0 to 2 pi, 0 to 1, and this simplifies to 6 minus 7 by 2 and minus 5 by 2. That is 7 by 2 minus 5 by 2. So it is minus 6 r square cos square theta, and from here minus 6 r square sin square theta multiplied by r by under root 2 dr d theta, which is equals to integration from 0 to 2 pi, integration from 0 to 1, 6 minus 6 r square into r by under root 2 dr d theta. So I can pull it this 1 by root 2 outside. Also, if you see that there is no dependence of theta here, and so we can write it as integration from 0 to 2 pi d theta and integration from 0 to 1, 6 minus 6 r square r by root 2 dr. So this simplifies to 2 pi multiplied by 1 by root 2. I can pull that out and it will be 6r minus 6r cube by 3, and limit varies from 0 to 1. So it is equals to under root 2 pi 6 minus 6 by 3, that is 2, that is 4, it is 2r cube. Okay, I did a calculation mistake here, so it will be 6r, that is 6r square by 2 minus 6r is 4 by 4. Our limit varies from 0 to 1. So it will be equals to under root 2 pi 6 by 2 minus 6 by 4, which is equals to, I can pull this 6 outside, so it will be 6 under root 2 pi 1 by 2 minus 1 by 4, which gives us 1 by 4 only. So it is 3 root 2 pi by 2, or that simplifies to 3 pi by root 2, or it is equals to 3 pi by under root 2. So this is basically the required volume that lies in between the two given paraboloids. So let's move on to the next question. So the next question says that find the volume bounded by the cylinder this and this plane and these two planes basically. So the required volume will be basically equals to volume is equals to triple integration dz dy dx, let's say, and the region is, let's say, like the region of which we are calculating volume is, let's say, R. So if you see that, let A be the basically the shadow region, and the z varies from 0 to 4 minus y, so it will be dz dy dx. So it is equals to integration A 4 minus y into dy dx. Now let's just reduce it to basically polar coordinates, so that will basically give us, for that we can assume x equals to r cos theta and y equals to r sin theta, and dA, which is dx dy, will be equals to r dr d theta, and here r lies in between 0 to 2 and theta lies in between 0 to 2 pi. So it will be equals to integration from 0 to 2 pi, integration from 0 to 2, 4 minus r sin theta into r dr d theta. So it is equals to integration from 0 to 2 pi, integration from 0 to 2, 4r minus r square sin theta dr d theta. So first let's just evaluate the inner integral with respect to r. So it will be equals to integration from 0 to 2 pi 4r square by 2 minus r cube by 3 sin theta, and r varies from 0 to 2 d theta. So it will be equals to integration from 0 to 2 pi 2r square minus r cube by 3 sin theta, and r varies from 0 to 2 d theta. So it is equals to integration from 0 to 2 pi 2 into 2 square, that is 4, minus 2 cube, that is 8 by 3 sine theta, and with respect to 0 it will be 0 only. So it is equals to integration from 0 to 2 pi 8 minus 8 by 3 sine theta d theta, which is equals to 8 theta minus 8 by 3 minus cos theta, and theta varies from 0 to 2 pi. So it simplifies to 8 times 2 pi minus 0 plus 8 by 3 cos 2 pi minus cos 0. Now this term reduces to 0 because cos 2 pi is 1 and cos 0 is also 1. So the final answer is 8 multiplied by 2 pi, that is 16 pi. So this is basically the required volume that lies in intersection of the given planes and the cylinder. So let's move on to the next question. So the next question says that find the volume of the region bounded above by xy plane, bounded by paraboloid and this cylinder. So this will be equals to, so it says that we are supposed to find the volume of the region which is above the xy plane and bounded by this paraboloid and the cylinder, like this cylinder. So it will be volume of required region will be equals to triple integration dz dy dx, let's say. So it will be equals to double integration, z varies from 0 to this x square plus y square dz times dA, and let's assume that A be the region for this area. So it will be equals to double integration over A x square plus y square dA. Now let's just reduce it to polar coordinates. So for that, let's assume that x equals to a cos theta and y equals to a sin theta, and from here dA will be equals to a, it's r sin theta and r cos theta. So dA will be equals to r dr d theta, and herein our r varies from 0 to a and theta varies from 0 to 2 pi. So this area will be equals to integration theta varies from 0 to 2 pi and integration r varies from 0 to a r square r dr d theta. So this simplifies to integration from 0 to 2 pi, integration from 0 to a r cube dr d theta, which is equals to integration from 0 to 2 pi. Integration with respect to r will be basically r is 4 by 4 and limit varies from 0 to a d theta, which is equals to a raised 4 by 4 integration from 0 to 2 pi d theta, and for that it will be 2 pi a raised 4 by 4, which is equals to pi a raised 4 by 2. So this is the final volume of the given region that we are supposed to evaluate. So in this question we are supposed to evaluate the volume that is lying inside this cylinder and outside this paraboloid, and it is also bounded by xy plane. So first let's simplify the equation of cylinder, that is x square plus y square minus 2x equals to 0. That simplifies to x square minus 2x plus 1 plus y square is equals to 1. So basically I just rearranged that and added 1 on both the sides. So it is equals to x minus 1 square plus y square equals to 1. So now let's just draw the figure of the volume that we're supposed to evaluate. So let's assume that this is z axis, this is x axis, and this is basically y axis. So our paraboloid will be of somewhat this form. Observe that it is passing via origin. This is passing via origin, and cylinder has center as 1, 0. So our cylinder will be somewhat of this form. Let's say this is our cylinder. So we are supposed to evaluate volume of the region that I am shading with black color. So we are supposed to evaluate this volume. Let's denote it with r. So the volume will be equals to triple integration over r dz dy dx. dx, that will be equals to double integration. Let this basically its shadow, let's this be a, so it will be double integration over a, and z varies from 0 to x square plus y square by 2 dz into dA, which is equals to double integration over a x square plus y square by 2 into dA. Now let's reduce it in polar coordinates form so that we can simplify our calculation a little bit. So let's assume that x minus 1 equals to r cos theta and y equals to r sin theta, and from here r dA will be basically equals to r dr d theta, and also observe that theta lies in between 0 to pi and r lies in between 0 to 1. So this simplifies to integration from 0 to pi, integration from 0 to 1. I can pull this 1 by 2 outside, so it will be x square, that is r cos theta plus 1 square plus y square, that is r sin theta square times r dr d theta, which is equals to 1 by 2 integration over 0 to pi, integration from 0 to 1. If I simplify it, it will be 1 plus r square cos square theta plus 2r cos theta plus r square sin square theta into r dr d theta, which simplifies to 1 by 2 integration from 0 to pi, integration from 0 to 1 plus, I can plug in combine these two terms, so it will be 1 plus r square plus 2r cos theta times r dr d theta, which simplifies to 1 by 2 times integration from 0 to pi, integration from 0 to 1, r plus r cube plus 2r square cos theta dr d theta, which is equals to 1 by 2 times integration from 0 to pi r square by 2 plus r raised 4 by 4 plus 2 r cube by 3 cos theta 0 to 1 d theta, which is equals to 1 by 2 integration from 0 to pi 1 by 2 plus 1 by 4 plus 2 by 3 cos theta d theta, which is equals to 1 by 2 integration from 0 to pi 3 by 4 plus 2 by 3 cos theta d theta, which is equals to 1 by 2 3 theta by 4 plus 2 by 3 sin theta, and theta varies from 0 to pi. It is equals to 1 by 2 3 pi by 4 plus 2, sin pi is basically 0, so that will be 0. Other terms will be 0 only, so it will be 3 pi by 8 cubic units. So that's the volume of the shaded region R. That is the region that's lying outside the given paraboloid but inside the cylinder. So let's move on to discuss the next question. So the next question says that the ellipse revolves about a x-axis. Find the volume of solid of revolution. So it says that basically, if let's say this is my x-axis and this is my y-axis and this is a equation of a ellipse and it is revolved around about x-axis, let's say like this. So we're supposed to evaluate volume of the solid that will be formed post the revolution of this ellipse. So basically we like this, the solid that will be formed will be containing these disc kind of form, and wherein, let me just make a bigger picture. So for example, like the solid that will be formed post revolution will be containing these discs, and if this is my x-axis, so this length will be y, which will act as radius. So we are just adding the area of these discs. So the volume of required solid will be volume of required solid is equals to integration from minus a to a pi y square times dx. Because this length is, we are assuming this as phi, and its area will be basically pi y square. And if you observe that this is major axis, its length is a comma 0, and here this point is minus a comma 0. So we are clubbing these kind of discs from this point up till this point. So that's why our limit varies from minus a to a. Now if you observe that this is basically symmetric around both x-axis and y-axis, so it will be same as writing in 2 times integration from 0 to a pi y square dx. Now using the given equation of ellipse, that is x square by a square plus y square by b square equals to 1. So this basically gives me y square as 1 minus x square by a square times b square. That is, my y square is equals to b square by a square times a square minus x square. So it simplifies my volume as equals to 2 times integration from 0 to a pi y square, that is b square by a square into a square minus x square dx. That simplifies to 2 pi b square by a square integration from 0 to a square minus x square dx. That is equals to 2 pi b square by a square x minus x cube by 3, and limit varies from 0 to a. So it is equals to 2 pi b square by a square a cube minus a cube by 3, and x is 0 only. So it simplifies to 2 pi b square by a square and 2a cube by 3. That is equals to 4 pi a b square by 3 cubic units. So this is the final answer of this question. So let's move on to discuss the next question. So the next question says that find the volume of solid above the xy plane and directly below the portion of elliptic paraboloid which is cut off by line z equals to 9. That is, we are supposed to find volume of solid above xy plane and directly below the portion of elliptic paraboloid which is cut off by line z equals to 9. Okay. So the required volume will be basically equals to triple integration dz dx dy. Now if you observe that the question states that, like, if this is my x-axis, this is my z-axis, and this is my y-axis, and there is a elliptic paraboloid. Let's say this is an elliptic paraboloid. So we are like the region of which we are supposed to evaluate volume lies above the xy plane and directly below this elliptic portion, that is below this, and this is cut by this plane that says z is equals to 9. So my z lies in between this top point to this point. So the volume is equals to double integration z from 9 to x square plus y square by 4 dz into dx dy. So it is equals to double integration x square plus y square by 4 minus 9 dx times dy. So it is, this is basically the, like, now we need to evaluate it. Now if you see that, like, in order to solve it I can change its variable. So let's assume that x is equals to 3v and y is equals to 3u and y is equals to, let's say, 6v. So the Jacobian will be basically equals to del x by del u, del x by del v, del y by del u, and del y by del v, which is equals to 3006, that is 18. So the given term reduces to double integration over x square, that is 9u square, plus y square, that is 36 by 4 9v square, minus 9 times 18 du dv, and u and v varies from basically, so this basically gives me double integration 9 u square plus v square minus 1 into 18 du times dv. Now if you see that using the equation of ellipse, that says that x square plus y square by 4 is equals to z, which is equals to 9. So if I just plug in these values of x and y, it will be 9u square plus 9v square equals to 9. So from here I got u square plus v square is equals to 1. So this basically gives me radius of the circle as 1. So u varies in between, like if I just reduce from here to polar coordinates, so it will be equals to double integration 0 to 2 pi 0 to 1 9 r square minus 1 times 18 r dr d theta. Like here I used it, like I used u and v to reduce it in polar coordinates, so it will be equals to 9 times 18 integration from 0 to pi 0 to 1 r cube minus r dr d theta, which is equals to 9 times 18 times 2 pi, and r is 4 by 4 minus r square by 2, and limit varies from 0 to 1, which is equals to 9 times 18 times 2 pi 1 by 4 minus 1 by 2, which is equals to 9 times, or maybe 18 times 18 pi divided by 2, and they will be divided by 4, there will be minus as well, so it is minus 81 pi. And since volume cannot be negative, so we can keep it positive as well, or what we can do is, like there will be negative sign herein, because the question says that the height lies in between this to this, and so our basically limit should varies from this point to till this point. So there is negative sign herein, here as well, so it will be positive and positive 81 pi. So this is basically the final volume of the given solid. So let's move on to the next question. So the next question says that find the volume of the region common to cylinder this and this. So this cylinder has axis as z axis, and this cylinder has axis as y axis. So we are supposed to evaluate the common volume of common region. So volume of common region will be equals to triple integration dz dy dx. Now from here you can see that z varies from 0 to, like basically z square will be equals to a square minus x square. So from here z will be equals to plus minus under root a square minus x square, so which is equals to z equals to minus under root a square minus x square and up till under root a square minus x square, that is dz. Likewise from here if you see that y varies from minus under root a square minus x square up till under root a square minus x square, and x varies from 0 to, like basically minus a to a, and it is dz dy dx. Now if you observe that cylinders are basically symmetric around the axis, so from here I'll get basically 8 times integration from 0 to a y varies from 0 to under root a square minus x square, and likewise z varies from 0 to under root a square minus x square dz dy dx. So it will be equals to 8 times integration from 0 to a, y is equals to 0 to under root a square minus x square. It is under root, if I integrate with respect to z, it will be a square minus x square dy dx, and there is no y in between in here, so it will be 8 times integration from 0 to a under root a square minus x square times under root a square minus x square dx. So it will be equals to 8 times integration from 0 to a square minus x square dx. So it will be equals to 8 times a square x minus x cube by 3, and x varies from 0 to a. So it gives us 8 times a cube minus a cube by 3, which is 16 a cube by 3 cubic units. So this is the final answer. So this question says that obtain the area in between this curve and its asymptote, that is x equals to 3. So the curve in the polar curve is in basically polar coordinates, but the asymptote is in Cartesian coordinates. So first let's draw the figure of curve. So it will be somewhat like this, and this is basically the asymptote, that is x equals to 3, and this is curve, that is r equals to 3 sec theta plus cos theta. Now if you observe that the given curve is basically symmetric along the x-axis, so it's like what we can do is we can just calculate the area of curve, area in between the curve in the first quadrant, and then we can multiply it with 2. So let's see how we can do that. So required area will be 2 times of area in first quadrant, which is equals to 2 times of double integration dA. Now if we reduce it in polar coordinates, this is already in polar coordinates, we need to reduce it. So it will be x, which is r cos theta, must be equals to 3. So from here we got r equals to 3 sec theta. Now it will be equals to integration r equals to 3 sec theta to r equals to 3 sec theta plus cos theta, and dA will reduce to r dr d theta, and theta varies from basically 0 to pi by 2, because we are in upper half, so it is 0 to pi by 2, and there is 2 outside, so it will reduce to 2 integration 0 to pi by 2. Now if we integrate it with respect to r, it will be r squared by 2, and limit varies from 3 times sec theta plus cos theta and 3 times sec theta d theta. Now it simplifies to integration from 0 to pi by 2, that is 9 sec theta plus cos theta square minus 9 sec square theta d theta, which is equals to, we can pull out 9 outside the integration sign, it is 0 to pi by 2 sec square theta plus cos square theta plus 2 times sec theta into cos theta, that is 1 only, so it minus 9 minus sec square theta d theta, and this sec square theta balances this one, so we are left with 9 integration 0 to pi by 2 cos square theta plus 2 d theta, and it will be equals to 9 integration from 0 to pi by 2 cos square theta can be written as 1 plus cos 2 theta by 2 plus 2 d theta, and this simplifies to 9 1 by 2 theta plus sin 2 theta by 2, theta varies from 0 to pi by 2 plus 2 theta, and here also theta varies from 0 to pi by 2, which is equals to 9 1 by 2 pi by 2 plus sin pi will be 0, again another terms will also be 0, plus 2 times pi by 2 minus 0. So this simplifies to 9 into pi by 4 plus pi, that is 9 into 5 pi by 4, which is 45 pi by 4. So this is basically the required area of the given in between the given curves. So that's all for today. We'll discuss the remaining questions in the next video. Thank you for watching, and please do like, share and subscribe the channel.